In today's lecture, we'll be looking at the synthetic division part of polynomial and synthetic division. So remember, our end goal is to be able to completely factor a polynomial and find all of its zeros. So with that in mind, we're really going to be using fact 3 here from our recall. So remember, if we have a zero of a function, this means that it's a solution to the polynomial equation f of x equals 0, and we're able to factor out x minus k from our polynomial and end up with something simpler. So we'll be dividing a lot of polynomials by these nice x minus k for some number k terms, and we'll be making them simpler. So we've come up with a technique that makes factoring only x minus k type terms very, very simple. So let's look at it. Alright, so we call this synthetic division. And we'll define the rules by just looking at an example of dividing ax cubed plus bx squared plus cx plus d by some nice linear factor x minus k. And we use the following pattern. So here, we take the numbers on our polynomial and we stick them inside this box here. So the a, b, c, and d are exactly the numbers multiplied by our polynomial. Then we take this minus k, whatever we're subtracting off, we flip the sign and we put that outside of the box. Once everything's in place, we just need to know how to combine these terms. The first step is we take our a term and we just write it simply outside of the box. And now we can start following our pattern. Any number outside of the box gets multiplied by k and brought back to the lower level of the box. Then we add these two numbers together, get some new number, multiply by k, put it back inside, add c to it, have a new number, multiply by k, bring it inside the box, add d, and we keep going until we have this r term on the outside. So the rule is that we add the entries in the columns and we multiply the number before the diagonal outside the box here, and we multiply that number by k, whatever we're dividing by. Now notation-wise, we say that r is the remainder of our long division. It's actually an important number, which we'll talk about in a couple seconds. For now, let's try doing one of these synthetic divisions. And we'll divide x to the fourth minus 10x squared minus 2x plus 4 by x plus 3. So remember, normally we write this as x minus k. So this is really x minus negative 3. And now we can put everything in its place. We have negative 3 outside, and then we just need to take the numbers multiplied by the polynomial and put them in order. If we don't have an x cubed term, which if you look we don't have here, then in the x cubed spot we put a 0. So this is 1, 0, negative 10, negative 2, and 4. The first one is for the highest, our x to the fourth power. Then the coefficient on our x cubed term, we don't have one, so we put a 0, x squared, x, and then our constant goes last. Alright, now that everything's in place, let's follow the rules. First we take 1 and bring it outside of the box. And now we can start our pattern. Whatever's outside of the box gets multiplied by negative 3, put up into the box, and then we start adding. So 1 times negative 3 is negative 3. 0 plus negative 3 is negative 3. Negative 3 times negative 3 is positive 9. Negative 10 plus 9 is negative 1. Negative 1 times negative 3 is positive 3. Negative 2 plus 3 is 1. 1 times negative 3 is negative 3. And 4 times negative 3, 4 plus negative 3 is 1. And we've done the division. Once we have things outside of the box, everything lowers by a power. So now this is our x cubed term. This is x squared. This is our x, our constant, and our remainder. When we want to convert this back into a polynomial, we do the following. We say x to the fourth minus 10x squared minus 2x plus 4 divided by x plus 3 is equal to 1x cubed minus 3x squared minus x plus 1 plus 1 divided by x plus 3. And these numbers match up exactly with the numbers outside of the box. And 1 is our remainder. So remember, for the remainder we have to divide by whatever we're dividing by to make that a nice fraction. However, it saves us this whole long division process, and it gives us what we want fairly simply. So let's talk a little bit more about the remainder, and we'll see some factor theorems as well. First of all, the remainder theorem says if we have a polynomial, f of x, and it's divided by some nice linear x minus k term, then whatever the remainder is should satisfy the equation that f of k is equal to r. What this means is if we plug in an x value of k, we should get a y value of r as our output. So synthetic division actually means we can evaluate our polynomial by just running through this process. So let's see it in practice here. Remember, this is x plus 2, so that means there's a minus 2 outside of the box. Then we have 3, 8, 5, negative 7. And we just start with our method here. Bring 3 outside. 3 times negative 2 is negative 6. 8 plus negative 6 is 2. 2 times negative 2 is negative 4. 5 plus negative 4 is 1. 1 times negative 2 is negative 2. And negative 7 minus negative 2, or plus, sorry, is negative 9. And what this means is that if we take negative 2 and plug it into our polynomial, then the output should be negative 9. So let's start by writing this polynomial in the factored form, and then we'll actually plug in negative 2 to make sure we have the right answer. So this should be 3x cubed plus 8x squared plus 5x minus 7 divided by x plus 2 is equal to 3x squared plus 2x plus 1 minus 9 divided by x plus 2. Again, remember these numbers match up with the numbers outside of the box. And if we wanted to, we could rewrite this and multiply the negative 2 on bottom here to the other side, this x plus 2. And if we do that, we get f of x is equal to 3x cubed plus 8x squared plus 5x minus 7 is equal to 3x squared plus 2x plus 1 times x plus 2 minus 9. When we multiply x plus 2 to the other side, it will cancel out with the denominator and the remainder. And now, if we plug negative 2 in to this equation, Then we get 3 times negative 2 squared plus 2 times negative 2 plus 1 times negative 2 plus 2 minus 9. But notice here that our negative 2 plus 2 term is going to be 0. So this equals 0, and that means that this is 0 minus 9, which is negative 9, which is exactly our remainder. So the remainder theorem makes sense, and really it's just saying once we factor, whatever we plug in for our negative 2 should just cancel out with the divisor, and only the remainder remains, which is, I guess, is why we call it the remainder. The final application we'll look at is the factor theorem. What the factor theorem says is that a polynomial f of x has a factor, x minus k, if and only if, when we plug in k to the polynomial, the y value is 0. Or in other words, the graph contains the point k0, and k is an x-intercept for our function. And this follows very nicely from the remainder theorem, because if f of k equals 0, then that means the remainder after division is also equal to 0. So let's put all this to use and completely factor a nice polynomial if we know what two of its factors are. So we'll factor f of x is equal to 2x to the fourth plus 7x cubed minus 4x squared minus 27x minus 18, knowing that we have two factors, or two zeros, already. Alright, so the first thing we'll do is we'll divide by one of our factors, and we can just start with x minus 2. Setting up, this means 2's outside of the box, and then we just write the coefficients of our polynomial on the inside. And we start our pattern. Bring the first 2 outside, 2 times 2 is 4, add to 11, multiply by 2 to get 22. Negative 4 plus 22 is 18. 2 times 18 is 36. Negative 27 plus 36 is 9. 9 times 2 is 18. And we have a remainder of 0, which means that we factored correctly. So now I can write this complicated polynomial in simpler terms. It's equal to x minus 2 times 2x cubed plus 11x squared plus 18x plus 9 with a remainder of 0. Remember, everything drops down by 1 power, so x to the 4th power becomes x cubed, and so on and so forth. Now we have another 0, so we can divide this polynomial by x plus 3 and get something even simpler. So we have 2, 11, 18, and 9. And we'll do our synthetic division again. 2 outside, negative 6 up, 5 down, negative 15 up, 3 down, negative 9 up, with a remainder 0. So now this cubic has become a quadratic, and we can say that f of x is equal to x minus 2 times x plus 3 times 2x squared plus 5x plus 3. And for our last step here, all we need to do is factor our quadratic, but we don't need any fancy division to do this. We can factor this on our own. So last step, factor 2x squared plus 5x plus 3. And our step says we multiply a and c together, and we get 6. Now we're looking for two numbers that multiply to be 6 and add to be 5. And actually we have our two numbers already, 2 and 3. 2 times 3 is 6. 2 plus 3 is 5. So we rewrite this to be 2x squared plus 2x plus 3x plus 3. Group them together. Pull out common terms. And now that we have the same thing inside the parentheses, we can factor that out. And we have x times 1 times 2x plus 3. So we can finish by completely factoring this. Our first term was x minus 2. Our second term was x plus 3. And our quadratic became x plus 1 and 2x plus 3. So we've pulled apart the original fourth power polynomial into 4 nice linear terms where we can get the zeros quite easily. So the zeros are x equals 2 from our first term here, x equals negative 3 from our second term right here, x equals negative 1 from our third term, and this one's a little bit tougher, but not too bad. X is equal to negative 3 divided by 2. And we have our 4 zeros. So maybe we can just finish quickly by graphing this. This was a fourth power polynomial, so 4 is even. Our an was equal to 2, which is greater than 1. Not 1, sorry, 0. So that means it rises on the left and the right. And our zeros are negative 3, negative 3 halves, negative 1, and 2. So the graph should look like this. Each time it's going to go through the x-axis, since we have a multiplicity of 1 for all of our zeros. And again, it rises on the right and the left. So there we have it. And that's the end of this lecture.